Welcome to Math 106, Chapter 4.4, where we're talking about the natural log. So I always like to start with the comparison between the exponential function and your natural log. So let's go ahead and look at your graphs here and see if you can pause the video and come up with the characteristics that you see on both graphs and then make a comparison. So first off, kind of split it in two. So we have y is equal to e to the x, the natural exponent. We also have y equals ln of x. This is the natural log. So first, let's take a look at what we might have noticed right off the bat. That might be your x and y intercept. So look at your x-intercept for your natural log or natural exponential, right? Well, do we have one? No, we don't have one. And we'll talk about why that is here in a moment. But if you look at your your x-intercept for your natural log, right? We do have an x-intercept that is 1, 0. And if we flipped it and said, okay, your y-intercept, well, we have one over here on your blue graph, and on your natural log, it doesn't look like we're going to have one. Now let's talk about why that might come up as to why we might not have an x-intercept or a y-intercept. Well, we already know for your natural exponential, or your exponential function, that we have a horizontal asymptote. We talked about why that was. So that was at y is equal to 0. So you'll notice that for your natural exponent, that we have a horizontal asymptote at y is equal to 0. And that is why we did not have an x-intercept. So if we look at your natural log, we don't have a y-intercept because we have another asymptote. This is when x is equal to 0. So we have x is equal to 0. So this is your vertical asymptote. At y is equal to 0. And that is why we do not have a y-intercept. And if we went on to talk about maybe your domain and range, you'll notice that your domain, right, all of your x values can be achieved. So we have all real numbers. Any number can go in for your x here. Whereas your range, because of your asymptote, right, your y values cannot start at 0. They can get as close as we can to 0 and then skyrocket up. And if we did the same for your other half, domain and range, your domain here for your red graph, or this pinkish color, is that your x values, they are not going to be able to cross this vertical asymptote. Therefore, you're not going to have any sort of x values. They can get as close as we can to 0 and then go up. Whereas your y values, they can get as negative as they want, and then they can reach up towards positive infinity. So this one is all real values as well. So what do you notice about these special features? Well, they should show you that you would have this kind of opposite effect, right? You don't have an x-intercept for your exponential, but you don't have one for your y-intercept from your natural log. And then these ones are kind of reversed. So they all look like they are reversed. Instead of a horizontal asymptote, you have a vertical asymptote. Your domain is swapped with your range and vice versa. Over here, there is a word for this when everything is completely mirrored. Now you'll notice that it is going to be completely mirrored over this line of y is equal to x. That means all of your x and y's have now swapped. That's why that mirroring effect works. These are called inverse functions. That they kind of swap one another. They undo that process, kind of like a square and a square root, right? So if you took, right, for example, x squared and you square rooted it, oh, well, you're just left with x. Or if you have a square root and then you suddenly square it, you're one more time left with x. That is because they are the reverse of one another to a degree. So for us, when we take a look at your natural log today, we'll notice that it's only available for your x values that are greater than 0. That is just saying no negative x values can go into your natural log. If you were to try to evaluate your natural log as a negative x value, you'll notice that it comes up with an error. In some calculators, they might be a little bit more powerful, in which case it'll tell you that it's what is it called? A complex number. So it means that if there's some sort of imaginary number aspect to it, which we're not going to be working with. So for us, your natural log is just y is equal to ln of x. And its complement, its reverse, this is the inverse, is x is equal to e to the y. And we're going to learn why that is right now. So there are a few different methods. The first one I'm going to use is the swoop method. And then once we learn one of your properties, I'll show you the other method. This is the one that I kind of prefer to use, but the first thing that we're going to do is learn just how to swoop and go into one form to another. So first, if we understand y is equal to ln of x, right? So y is equal to ln of x. When we go to swoop, and you can do it in either case, you can swoop left or right. Some cases, when I first get started, I'm over here, right? But when we do start, you always start on your base. Now, the base of ln, we haven't talked about this quite yet, but the base of ln is e. That is because it's wanting to match this one over here. And maybe I should swoop starting from the other one. So maybe I'll show you that way. So if we have x is equal to e of y. So when you go to swoop, you always start on your base, which we now know here is base of e. And we're going to go up and around. We're going to touch x, and then we land on y. So whatever you start with first, or the order in which you touch or you start, is the order in which you write. So your swoop method here, to go from an exponential into a logarithm, we're going to first write the word ln or log. For us, because we're dealing with e, we're going to just write the word ln. With our base of e, this is the very first thing that we're going to write. So this is the very first thing we're going to write. And the next thing that we get to write is your next value that you touch. That would be x here. So that is number 2. So you have number 2 right here. And then equals your y. This is the third thing that you finish on. So to do the swoop method, you always start on your base, right? So when you first write it, you need to write some sort of log, whether that's ln or that's your log. And you write your base. For us, we have a base of e for today. So ln of e, that's the first thing that we started on. Come up and around, that is your next value that we write, is equal to, therefore, your very last one of y. And you'll notice that you have to cross this equal sign. So that's kind of why we write that equal sign here. You don't really, I mean, you could say you crossed it twice, but we're going to say that that doesn't actually happen. Now, to go to the reverse of it, if you have y is equal to ln of x, we now know that the base of ln is e. And I'm going to write that over here. Base of ln is e. This is your natural log. So you start on your base, right? In this case, we're going to come up and around to y and then land on x. So this is number 1. This is number, number 2, and this is number 3. So we write your base e, that was number 1. Then you go up to your exponent, this is number 2, is equal to the last one is x, that is number 3. So they should look very similar to one another. So that is your swoop method. We're going to practice that right here to get you guys into kind of the hang of it. So let's just try these first 2 quick examples. And you'll notice that it's not always just x. X can have some sort of parentheses around it. So this is kind of just modeling a shift in your graph. And for now, let's just keep writing the hidden e that's located in your ln. So swoop, right? We start on your base. We come up and around 4 and land on x. If you don't like the way in which it's written, notice that we swooped the other side. You can always write the 4 on this side or the 3 on this side. It doesn't really matter which side you swoop to, but we always want to land on your kind of close to ln once more. So first thing we touched was e, and then 4 is equal to x. Or on your other case, e cubed is equal to x plus 2. Now, if we were asked to just convert, great, we are done converting, right? We are done converting. But if it asks us to solve, we want to get x to one side. So for us, that first one, we were done. X is now alone on one side. But for your second one, your x is still kind of trapped, which means that for your next part, we can go ahead and drop your parentheses here and start solving for x, in which case there's one more thing we need to do, which is to subtract 2 to the other side. So e cubed minus 2 is equal to x. So this one we have converted. And this one we have solved. I'm going to give you a couple more quick examples before we approach C. Oh, there's lots of them here. So let's have you guys try. Let's have you try number 3, number 11, 13, 14, and then number 4. So just a couple of those. So pause the video, see what you come up with. So if we have your base here of e, right? We start on your base, come up and around, and land on your exponent. So this is number 1, this is number 2, and this is number 3. Now to go from an exponent into a logarithm, we need to write the word log, or in our case, if we have a base of e, we need the word ln. Base e, that was number 1. Number 2 is 12, is equal to x. Let's do it again with number 11. Actually, let's do it one more time with number 4. You'll notice that we have this 5 over here, so we might want to consider dividing everything by 5 to start. So ex is equal to 36 over 5. And now that your e is all alone, right, and we can do your swoop, number 1, number 2, and number 3. Again, to go into a logarithm, we need to write ln. And because we have a base of e, right, e is with your ln. We have 36 over 5 is equal to x once more. Now to do the opposite, right, something like this, ln has a secret little e, so we'll put those in there. Come up and around, come up and around. So you have e squared is equal to x, or e squared is equal to x minus 3. And then we need to solve. Plus 3 is equal to x. And one more, hidden little e here. E to the 1 is equal to 4x. Divide everything by 4. e over 4 is equal to x. And again, there's some more examples for you guys to work on. I'll leave number 1 and 2 alone just for now, and we're going to talk about those cases in a minute. And again, maybe even we try a few more on this worksheet. So let's have you guys start with C. Right, on our worksheet, we said, hey, we're going to try to get your exponential all alone or your logarithm all alone. So notice that e has this coefficient. So let's go ahead and divide this coefficient really quickly. So we have 4 is equal to e of 2x. Now that e is all alone, and notice that we're working with e and ln as a base of e. So if we have a base of e, we're going to write the word ln first of e. So we can swoop. Again, if you don't like the side that you're swooping to, that's okay. But this is number 1, number 2, and number 3. So ln of 4 is equal to 2x. Solve for x. Let's divide everything by 2. And you'll notice that I'm going to divide everything by 2. That is because ln of 4 is a number. And I'll show you that here. We'll correct. Let's see. Where's my ln? Make the function over here. Ln of 4. So ln of 4 is about 1.4-ish. So this is a number. So about 1.4-ish. So you would have to divide this 1.4 by 2. So you'll notice that if, right, on accident, if you divided ln of 4, let's see, where is it? ln of 4 divided by 2. That just means ln of 2, right? Oops. Right, we get 0.693, right? So this is just ln of 2. Now, if we also did it the other way, right, the correct way, we said ln of 4 divided by 2 here. You'll notice that there's no consequence, but that is just because the relationship between 4 and 2, right? But if we were to swap it, right, and let's say you on accident, instead of dividing by 2, let's say it was ln of 4 is equal to 3x, right? So if you divided 4 by 3, you'll notice that we get 0.287-ish, whereas that's the incorrect one. So if we take ln of 4, which is its own number, we said that was about 1.4 itself. And if we divide that by 3, notice that it comes up with a different value, right? The second one is your correct value because we are taking ln of 4, which is a number, and dividing that by 3. So while it might look like, hey, there's no consequence to me dividing the 4 and the 2 together, right? In some instances, you're right, there isn't quite a difference, but that is just like a very special case where you can kind of just do like a really quick cheat, whereas typically it does not actually work. So now let's move on to example 1, right? We're going to keep stepping it up a degree and maybe come up with a step-by-step process. So in this process, right, instead of swooping right away, right, number 1, we have to get the exponential or the logarithm alone to one side. So here we get it alone into one side. So that means we need to get rid of your coefficient. So divide / multiply your coefficient. If you have anything that's added or subtracted, we could also do that as well. And that's usually something you want to do first. Add or subtract a constant. Number 1, A, number 1, B, divide by your coefficient. So for us, we now have e to the x minus 3 is equal to 4/5. Now step 2 is we can put it into a logarithm. So we can swoop. We have to write ln first of e of 4/5 is equal to x minus 3. And then step 3 is to solve for x. ln of 4/5 plus 3 is equal to x. We're going to do it one more time with example 2, just by copying these ones down. All right, let's have you try example 2. So now we're working with a logarithm, right? We're working with ln. So first thing we need to do is move your constant to the other side, right? That is number 1, a. So add or subtract your constant. So for us, we need to subtract 7 to the other side. Get your log all alone. Now that it's all alone, we can go ahead and divide by your coefficient. Now we can put it into your log by swooping, right? We have a little hidden e here, come up and around and land on x. So you have x, oops, so sorry. We have to write e to the negative 7/2 is equal to x, and then we fully solved it. So you can, if you want to, take it a step further and put e down in the denominator and make it positive. So far, right, we've been just talking about using this swoop method. But as we use your swoop method, we can also come up with another method by solving for some properties, right? And now just recall some of your properties of your exponents, right? So if we have properties of exponents, we could say, hey, this is x to the a times x to the b, right? What did we normally do here with this exponent? We said, well, we added your exponents, right? So if we were to approach this from a standpoint of putting them into a logarithm, right? ln, kind of base of e, right? m times n. Notice that we have that multiplication on the inside, right? I'm just going to make it a very obvious multiplication like I did here, right? But we can break this apart and we can bring them to have their own ln, and we're going to add them together. Just like you did with your addition over here. We're just going to add them together so we can break them apart. And let's do your other one, right? Your little quotient rule, x to the a over x to the b. What did we do then? We said a minus b. So one more time, if we put it into your logarithm form, we have m over n, so some sort of division. One more time, we can break it up to be ln of m minus, just like the b is doing the dividing that was on the bottom, your n is going to do the subtraction, that dividing. And last one, right, we said where we had x to the a raised to the b, right? Well, we said, hey, we're going to multiply these two together. So for us, if we have ln, again, base e, of m to the k, where k is now your exponent of sorts, this one is nice because we're going to show that, hey, they are going to be multiplied. So k is going to come out front and be multiplied to your logarithm. So that little multiplication symbol comes out here. So let's practice those really quick. Let's do just a couple of these over here. So let's do number 1, number 2, number 4. Let's just do those first few. So if we were kind of going in that reverse aspect, right? Notice that we have your 15, right? Your 15 is really your k. So these ones get to come up on top of your function here. Same thing, 3 gets to go up on top of your b here. So we have log base 5 of a to the 15. That is your k. That was your exponent. Plus log of 5 b to the 3. Again, that was your exponent. So now with this addition sign, right? With the addition sign, and even better, we can only do this as long as we have the same exact base. These are in the same form of a logarithm. So we're working with properties of logs. So the ln that I wrote down is going to run through even with the logs that you're seeing here. So we want to condense this into one logarithm. So we have log base 5 of, instead of a plus sign, right, it's going to turn to a multiplication between a and b, a to the 15 and b squared, or b cubed. And you can put parentheses around these if you want. Let's try it again one more time. So here we have 4 on the outside. Let's bring it up top here. 6 on the outside. Let's bring it up top here. So we have log base 4 of u to the 4th minus log base 4 of v to the 6th. So those go up top. We have the same exact logarithmic base, so we can combine these. These are like terms. And we had a subtraction sign. Subtraction, we turn into division. So we're going to try to get this one logarithm of base 4 into some sort of a division. And we said whatever is doing the subtraction is doing the dividing. So we should have v6 down below and u to the 4th up above. And again, we cannot go any further because we are working with v and u. Let's try it again with number 4. We have 2 that can come up, 8 that can come up. So we have log base 2 of x squared plus log base 2 of y to the 8th. Again, these are the same exact base, so these are like terms. So we're going to write one of these logarithms. And now we're going to try to combine these values. So we have an addition sign, which addition turns into multiplication. So it's the multiplication between x squared and y to the 8th. Just like you had your division here, this multiplication, that addition, multiplication. I feel like I highlighted one more. Let's try it again with maybe just one more. With 10, and then we'll do the reverse. Let's do 12, let's do 13 and 14. All right, these come up, these come up. Log 6 x cubed minus log 6 y to the 6th. They both have a base of 6 here, so that is exactly what we want. We go from a subtraction, so we're going to go try to get one of these log base 6's. Subtraction turns into division. Whatever is doing the subtraction does the dividing, so we have y to the 6th, and x cubed comes up above. Now, when it comes to breaking them down, right, we have to figure out, okay, well, what's the primary operation between the two? So here in number 12, you have x to the 5th times y squared. So that multiplication symbol turns into an addition symbol. And we're just adding multiple logarithms. So we have a log of base 4. So we have log base 4, log base 4. And we get to write these two that are being multiplied now added together. And the last thing we might need to do is your exponents. So those exponents get to come right down in front. So this should be 5 log base 4 of x plus 2 log base 4 of y. Let's do it again with number 13, and then we'll try out 14. So here one more time, we have multiplication. Actually, do what I want. We're also going to do one with division. So we're going to do 16 after that. So here, right, we have multiplication. So that is going to turn into addition. Addition between two logarithms of base 2. So that would be x squared and y to the 5th. And we're going to bring those exponents down to be 2 log base 2 of x plus 5 log base 2 of y. One more. Now you'll notice that we have this squared. So the very first thing that we need to do is bring that squared out in front. We're going to use a parentheses here. And now you have that multiplication, which then turns into addition. That 2 stays out front. So we're going to write 2 log base 5s. And the more operations you have, the bigger it's going to become. So you have x, you have y to the 5th, and then of course bring that 5 out front. And there you go. We're going to do one more with division. So pause here, see if you can do it. So we tried the very first one with, or like 14, right? We want to bring down your exponent first on the outside. Log base 7, u to the 4th over v. Now we have division, and we want to turn it into subtraction. Subtraction between 2 of these log base 7s. That 6 just remains on the outside. So whatever's doing the subtraction was doing the dividing. We have u to the 4th here. And one more, we're going to bring that out in front. So you have 6 times 4 log base 7 of u minus log base 7 of v. So now we're going to kick it up a notch with our quick simplification, and then we're going to get into the remaining 3 or 4 properties. So here, right, we have addition. Addition, we said, is going to turn to multiplication. So we're multiplying x and y. We also have division here, or subtraction, which is going to turn to division. So that w comes down. And we are doing one logarithm, so that would be just one of these ln's. Let's try it again over here. We have a 4 up front, so let's put it up onto your ln of 2. And notice that it's only, it doesn't have a big parentheses, it's just going to this ln of 2. So we have ln of 2 to the 4th plus ln of x. 2 to the 4th is 16. So you might want to simplify that. We have addition, which is going to turn to multiplication between 16 and x. And we're just looking for one ln here. So we have ln, and I'm going to write it one more time a little bit nicer, of 16x. Now, if these were kind of out of order, I like to make sure that all of my subtraction signs are going to be going down, like kind of down the roll. So if you see a negative sign out here, I would just put it at the end, because if you can tell, okay, here is a negative sign. So what these 2 items have in common is a negative. So I can go ahead and factor out that negative and make it positive. And now I can go ahead and get started. Okay, this can come up, this can come up. We have ln of 1, which we'll talk about here in a second, ln of 3 minus ln of 5 plus ln of y to the 4th. Oops, 3 cubed. There we go. Now, looking at ln of 1, right? Can you guys, we haven't seen this property yet, but can you go ahead and swoop for me? And I'm just going to put my variable x here for a second. So if we were to swoop, this is just saying that we have e to the x is equal to 1. So what does that make x? Well, that makes x 0, right? Anything to the 0 power is equal to 1. So if you see ln of 1 or a log of 1, that is just going to say that this is actually really equal to 0. So this is just a non-existent term. So instead, right, we don't have to write this term any longer. So it's just ln of 3 cubed, which is ln of 27, minus ln of 5 plus ln of y over 4. So let's see if we can keep combining into one ln. So let's focus on this addition sign. We said addition turns into multiplication. So right here we have ln of 5 times y to the 4th. And this whole thing is being subtracted by ln of 27. So that subtraction sign is going to turn into a division sign. So we have ln of some sort. We're going to be dividing by anything that was in the denominator, so that anything that was being subtracted ends up in the denominator. So you'll notice that we have 5y to the 4th doing the subtraction, so it's now doing the division, and 27 is now up above. Now there's no correlation between 27 and 5, so we don't have to simplify any further. So right now, we're almost done. We just learned that ln of 1 is equal to 0, because if we did that swoop, we said e to the x is equal to 1, therefore x is equal to 0, e to the 0 is equal to 1, right? So there are a couple properties like that. If we said, okay, maybe if we have something on the outside, let's say ln of e is equal to, and I'm just going to put x here. Can you go ahead and swoop this one? Well, to swoop, right, we have e to the x is equal to e. So what does that make x? Well, this e has an exponent of 1, so that just means that x is equal to 1. So it just says e to the 1 is equal to e to the 1st. So that means that if we see ln of base e that's evaluating e itself, they have now undone each other, and you're left with just 1, or your exponent. They end up canceling each other out, this one and your next few. So I'll write another one. We have ln of e to the x is equal to, and I'm going to say equal to what? So again, if you swoop, we have e to the something is equal to e to the x. Therefore, x is equal to something, right? X is equal to x. E to the x is equal to e to the x. So again, they kind of undo each other. So these will cancel out and leave behind some sort of exponent. Your exponent ends up dropping. So we'll replace that with x. And its opposite counterpart is if instead of taking your logarithm first, but instead we take your exponent first. So we have the exponent, e, base e, raised to the ln of e to the x. Well, because they cancel each other out, right? These keep canceling each other out and letting your exponent drop. This will also equal to 0. Those three properties can tell us that these are your inverse properties. These three are your inverse properties. Much like if you do x² and take the square root of it, right, you're left with x. You're left with 1. you're left with x, you're left with x. Or again, maybe you take the square root and then square it. Again, you're left with x. This is just a different form, right? That is this format here, and these two can be that format. So instead of using your swoop method, we can use this property of your inverse. This is what I prefer to write with, is using this inverse property. So if we were to do the reverse over here, right? If we had ln of x is equal to -7/2, instead of doing your swoop, we know that your base is e here. So as long as I match my base e, and if I do it to one side, I also have to do it to the other. That allows me to cancel on this side. It undoes that process and leaves x behind. So my x drops. So I'm left with equals to e to the -7/2. If I were to go kind of backwards, let's say over here, right? You have, I'll pick it up before we do your swoop here. E to the x minus 3 is equal to 4/5, right? Well, to undo your e, because your exponent, right, is up, your variable is up in your exponent. So as long as I write ln of base e, that matches that e. And if I do it to the other side as well, again, it cancels and it allows this x minus 3 to drop. In which case, I can then go ahead and add my 3 to the other side. And I would fully solve it. So if you like your swoop method, use your swoop method. You're going to be seeing me write this method a lot more, just because a lot of the times when students use the swoop method on your exponential, sometimes you end up writing e to the 4/5 is equal to x minus 3, but you didn't go from an exponential to a logarithm. You went from an exponential to another exponential, right? It's not undoing that process. So that's why I like this, this method, because it forces you to write ln. And if you wanted to, you could do it here as well. Notice that e to the ln of x, well, that has your base e here. So they will cancel and x drops. So x is equal to 4. Or if you wanted to do your swoop method, that's fine. It's just ln of base e, e of 4 is equal to ln of e x, right? There's a lot going on, right? So therefore, x has to be equal to 4. Or here, right? Again, another e is here. So they cancel, your 3x drops, and you have 24, in which case you can divide by 3, and x is equal to 8. Or if you were to do it again, let's see if there's a quick one over here, right? If I know my base here is e, I can write my base of e, and I can cancel. X squared is equal to e to the 10th, in which case x is equal to the square root of e to the x. Keep in mind, we start with an exponent or a logarithm, so you have to be careful with your x values, right? But in our case, we're not fully finished, right? E to the 10/2, well, that would be 5. And keep in mind, we know that the square root can be written as 1/2, so that's why that is there. So we have e to the 5th. Or sorry, that is e to the 5th. Yeah, x is equal to e to the 5th. So I like using that property a lot more. So let's have you guys get into the hang of it with example 3, kind of doing a combination of those. First, try and simplify it into one log if you see multiple, and then take your property where you can just write to cancel out your exponential. So here we have addition. So we're going to write e ln. Addition turns to multiplication. So we're multiplying 4 times 5. So we have e to the ln of 20. But we know ln has a base of e, so these can cancel, and our 20 drops. So really, this is just 20. Here we have subtraction. So of e to the ln. Subtraction turns to division. 3 is doing the subtracting. So we are doing the dividing. And again, we have your ln here, which has your same base. So it drops, and we have 4/3. Over here, we have 2 being raised up to the 4. So we have e ln of 3 plus ln, let's see, 4 squared, that's going to be 16. Now we have to take care of that addition sign, which turns into multiplication between 3 and 16 and writing one of your ln's. So we have e ln of 48. And because ln has a base of e, they are going to cancel, and your 48 drops. Here, keep in mind, it's kind of the reverse aspect of it. You see division, right? In which case division is going to turn to subtraction. So subtraction. So some sort of a subtraction between your ln values. So subtraction between ln of 1 and ln of e squared. Now think about this one, right? ln of e, that will allow us to cancel in this drop. So we have -2. ln of 1, we said ln of 1, if we're confused, we can just set equal to x. And you can do your swoop method if you like. So e to the x is equal to 1. Therefore, x is equal to 0. So e to the 0 is equal to 1. So we have 0. In our case, we're equal to -2. And I believe that is it for today using those properties. If you want, you can kind of go back to this page and kind of hone in your skills. I think the answer key is over here. Nope, that's just a few more. And now your answer key. Here you go.